Well, thank you very much for staying until the last second of the conference. I promise I'll try to make it as enjoyable as possible. So this talk is about also flow sensors, so thermal flow sensors for medical applications, and we have also made them flexible, as I will show in this talk. The outline is as follows. I will first start with a small introduction, then present what we've done before. Then we quickly go through the design and fabrication of the sensors, and then present the results we had. We finish with some conclusions and the future work, or more the ongoing work. So, well, the introduction of the last talk is pretty much the same as this one. You have CADs, or arteriosclerosis disease. It's one, if not the main leading cause of death in our society today. So what you see here is the healthy hearts with a healthy coronary artery. The coronary artery is the artery that feeds blood to the heart muscle. Well, if you have a disease, so if you eat too much, for example, or drink too much, or have not a very good lifestyle, then you have buildup of plaques on these artery walls, and that can eventually lead to the blockage of the artery. And based on that, you can have a heart attack. That's something that you don't want to happen, because you most of the time die from it. So the main standard diagnosis procedure is an Xray angiography, where the doctor makes an X-ray picture of your coronary artery, and you see here clearly. So this is the artery, and you can clearly see here stenosis. But the drawback from this method is that you make a 2D projection out of 3D geometry, so that can lead to under or overestimation of the stenosis. Another type of diagnosis, as you said again, is in situ measurements. So you can, what the doctors do, you make a small incision in the groin, and you bring a catheter up to the area where you have the stenosis. In this catheter, you can find lots of those commercially available with pressure, temperature, pH, flow, even images included at the tip of these catheters. However, the diameter of these catheters is quite large compared to the diameter of a coronary artery. But the doctors always, before inserting the catheter, insert what we call a guidewire, which is, as the name says, used as a guide. And these guide wires are very, very thin. They are 360 micron diameter. And that would be great to be able to include all these sensors on the guide wire. There is one commercially available guide wire from St. Jude Medical Systems that contains a pressure sensor at its tip. And the idea, our idea, is to include a flow sensor with it, because it is very important for doctors to have the dynamics of flow and pressure at the same time. Our idea is to basically band a flow sensor, thermal flow sensor, around the guide wire, connected inside the silicon chip containing the pressure sensors. The pressure sensor, the electronics if needed, and the bondpads to go to the outside world. That would allow for quick and easy assessments of the severity of the stenosis. So the previous work, we have previously reported a fully flexible thermal flow sensor, flexible to a diameter of 3 mm, which is good, but obviously not good enough for being included at the tip of a guide wire. We have also shown that this flow sensor is very able to follow coronary-like flows, and then we have also showed how to improve this flow sensor, the design of the flow sensor, to make it flexible to such small diameters. So this is the flow sensor. It has 3 main components. The first one is a heater. There is a small heater ring around the diameter of the guide wire. Except that compared to the previous talk, this time we also add 2 thermopiles, polysilicon-based thermopiles. The first one measured temperature difference between a small point upstream from the heater, and the second one downstream from the heater. And the second thermopile measures the temperature difference between the heater itself and the point far away upstream, which we call T fluid. So it's measuring the temperature of the fluid, the temperature difference between the heater and the fluid. So in the end, we have 3 signals that we can use for our flow sensor: the 2 output voltages, T down, T up, and T heater, T fluid, and the power you supply to the heater. Operating modes. There is one way of operating, which is constant power, where you supply the heater with a constant power, and then you measure the output voltages of the thermopiles, and they are measured for the flow, or the shear rate that you can translate to flow. It is an easy measurement because you don't need electronics for the easy measurements. But as you mentioned, also you can have very high overheat temperatures at low flow. So you have low flow, temperature is not brought away from the heater, and the heater will heater temperature will rise. It's not something you want when you go inside the arteries. And also when you go to high flows, is the opposite that happens, is that the temperature of the heater will actually decrease a lot because of the high flows, and then the temperature difference between the heater and the fluids is very small. Thus you decrease the signal to noise ratio. So another driving mode is keeping the temperature difference constant. So this time you keep the temperature difference between the heater and the fluid constant, and you measure the power you need to the heater to keep it constant. And this is the measure for the flow. The T down, T up thermopiles gives us the direction for the flow. The disadvantage is that you need a feedback loop, so you need to add some electronics together with the sensor. But the huge advantage for medical applications is that you can set yourself the overheat temperature, so you can put it as small as you want. The fabrication, I will go quickly through it. This is not the point of this talk. I will just mention that it has been fabricated using a dedicated technology for flexible devices we call F2R technology, in which you can just basically pick up your devices out of the wafer and mount them into the catheter or guidewires if you need. So these are the sensors after fabrication. You see here the flow sensor, and here a silicon chip with a pressure sensor and the bond pads for wire bonding. This is a handing stripe that we use for the mounting that we can just remove by cutting those small polyimide hinges afterwards. So the mounting, we first characterize those on PCB. So this is a PCB with the three flow sensors here. This PCB has a channel, so it has kind of a groove, and you have the flow sensors over the channel. Then they're connected to connectors that we can go to a readout inside a computer. And then we cover this channel with a glass plate. Here we have an input and output, inlet and outlet for the flow, and then we can go on with our measurements. So measurements. First, we of course electrically characterized our sensors. The TCR of the heaters was well, as follows, and there is no hysteresis between going up and down in temperature. And for the Seebeck coefficients of the polysilicon thermopiles, we actually used a dedicated device here. It consists of two heaters, so two heaters on each side, and then a thermopile measuring the temperature difference between two heaters. One heater is used as a heater, so we heat, and the other one is used as a temperature sensor. Once you have characterized the TCR, you can use it as a temperature sensor. So we know the temperature difference between the two heaters, and we can measure the output voltage, and thus we can go back to the Seebeck coefficient of the thermocouples. So let's go on with the results. So these first experiments were done in constant power mode. We kept the constant power power constant at 10 milliwatts, and this is done with a steady flow experiments. The red curve here is the T heater, T fluid output voltage, and you see that it is, well, decreasing, as I said before, to very low values at high flows. This is not something that you want. For the T down, T up thermopile, it is nicely increasing, but after a while it starts to decrease, meaning that for two different values of flow, for example 6 here and 1.5, we'll have the same output value, output voltage. This is not something that you want. However, if you combine those two output voltages, and you take the ratio of the two, you get a nice increasing curve that you can use for flow measurements. But well, what is maybe more interesting for us for medical applications, it's constant temperature mode, constant temperature difference mode. So we set the overheat temperature to 5K, which is quite low and acceptable for medical applications. This time we had steady flow experiments, so with the 1 Hz flow frequency, which is the base frequency for the blood flow in the arteries, in the coronary arteries. We see two things. The first thing is that the control system for the CTD mode works well, but is not fast enough. How do we see that? Is that here, so in red, you have the T heater, T fluid output voltage, which will stay constant because this is how we drive the sensor. However, you see that at low flows, so the flow is in green. You see that at low flows, this temperature difference increases. This is due to the fact that since our feedback loop is not fast enough, it is not fast enough to actually cool down the heater at low flows. The second point that we see is that the T fluid point is too close to the heater to actually act as a perfect reference temperature point. We see that here. So ideally, if everything was perfect, whether you have a forward flow or backward flow at some value, so here minus 80 milliliter per minute or plus 80 milliliter per minute, the power you need to supply to the heater should be the same. Whereas here, the power you need to supply is actually higher for back flows. This is due to the fact that since the fluid point is not far enough from the heater, when you have backflows, you bring heat to the heater, to the fluids. So the T fluid increases. Thus, you need to increase also the temperature of the heater to keep it constant. However, we have been able to follow coronary-like dynamic flows quite well using this technique. You see in green here the reference flow meter we had for experiments, and in red what are our results. I think they are quite good. In conclusion, so we have designed and fabricated thermoflow sensors especially made for blood flow measurements inside the coronary arteries. The fabrication has been done using a dedicated technology called F2R, and we have mounted and tested those on PCB channels under both steady and unsteady flow with both constant power and constant temperature mode. The CTD mode is more sensitive and also safer for medical applications. So the results are very promising for the combination of pressure and flow at the tip of the guide wire. As a future work, of course, we want to test those sensors bent around catheters and guide wires. As I said previously, that it's not future work, but it's ongoing work because we've actually mounted those sensors here at the tip of a 1 mm diameter guide wire. You see here the slits for the foil to go inside, connected to the chip inside, and also at the tip of 360 micron diameter guide wires. You see how small it is compared to a normal match. So hopefully I can present these results in a special issue of the IEEE Sensor Journal later on. I would like to thank you very much.